Hello students, myself Manuj from Scholars Forum. Again I welcome you all to this homemade video series of class 11th and class 12 topics. In the previous video we discussed about the numerical aspect of colligative properties. Link you can find in the description. And in this video we will be discussing about some more topics like ideal solution. Okay, one more thing, please solve all the DPPs till I gave you this moment. And we will be discussing the doubts if you will ask me. Okay, now what is ideal solution? Ideal solution is the solution which follows Raoult's law for all composition possible. Okay, means it doesn't matter what composition of mixture you are having or what composition of solution you are having, your Raoult's law will be applicable in all composition. It will be applicable in all composition. So such solution we call ideal solution. Okay, definition is clear. जो solution Raoult's law को पूरी तरीके से follow करता है, we call that ideal solution. Now, let's say, suppose we have A and we have B. We have added V1 volume of A and V2 volume of B, and we have tried to form a solution. Okay, I hope you can see here A, V1 volume, B, V2 volume, and we have formed a solution. Now, if I talk about this solute A or solvent, doesn't matter. If I just talk about this A, so how many type of interaction I will have here? If I have just only A molecule, A type of molecule. So here I will have just AA interaction. A will be interacting with itself. Okay. Now here what will happen? B will be interacting with B only. So I will have here BB interaction. Okay. Now in this solution, what I will have? I will have some A which will be interacting with A only. Similarly, some B who will be interacting with B only. And some A who will be interacting with B as well. Are you getting this thing? So I will have three type of interaction. A, self-interaction. BB, self-interaction. AB, cross-interaction. Is this clear? Now, if I want to form AB interaction, I will have to do these things. What are these things? Let's say I will have to break AA interaction. Is this clear? And whenever I break any interaction, means whenever I break any sort of bond, energy is consumed. So let's say energy required here is delta H1. So delta H1 is what? Positive. It will be endothermic. Similarly, I will have to break BB interaction as well. So BB interaction will be broken, and here energy required enthalpy changes. Let's say delta H2. Delta H2 is what? Again positive. Clear? Now some of A have broken their interaction, some of B have broken their interaction. Now it's time for cross interaction. Now if you form AB interaction, so energy will be released because you are forming an interaction, you are forming a type of bond. So delta H3, let's say in enthalpy changes, it will be negative. Now what will be delta H mixing? Delta H mixing will be delta H1 plus delta H2 plus delta H3. Clear? Now, since you added here V1 volume here and V2 volume here, and let's say solution volume is VF. So what will be delta V mixing? Means what is volume change during this process? Volume change will be final volume, means VF minus initial volume, V1 plus V2. Are you getting this thing? Now, for an ideal solution, if you want an ideal solution, so first condition is this delta H mixing, it will be 0. This must be 0. Delta H mixing means, let's say energy required in breaking this A interaction is 80. And let's say energy required in breaking this BB interaction is, let's say 60. So total energy required for breaking the interaction, it will be 140. So how much energy will be required to form this? How much energy will be released for formation of this, AB interaction? It must be minus 140. If it is not minus 140, so net delta H will never be 0. Are you getting this thing? Means no net change in enthalpy must be there. Clear? First point. This is the first condition for ideal solution. Now second, what was delta V mixing? Delta V mixing was V final minus V initial, and let me tell you, this should also be 0. Means there should be no change in volume occur when we add V1 volume of A and V2 volume of B. Means if I add 50 ml from here, 60 ml from here, so net volume I should get 110. It should not be greater than 110 and it should not be less than 110. Clear? So these two conditions are there for any ideal solution. And of course, this solution condition will be there. Delta S mixing will be greater than 0 and delta G mixing will be less than 0. We have already talked about this. Okay. So if you are following these conditions, your solution will be ideal. And it will definitely follow Raoult's law. Clear? Now let's check some example here. Example is N-heptane and N-hexane. See, both are similar type of molecule. So generally similar type of molecule form ideal solution. Okay. And let's say bromoethane and iodoethane. See, again similar type of molecule, isn't it? Benzene, toluene. Both are aromatic. Okay, let's take one more. Chloroethane and bromoethane. What do I mean? When similar type of molecules are mixed, they generally form ideal solution. Okay, and let me tell you one more thing. So as there is no ideal in this world, there is nothing such as ideal exists in practical life. There is no ideal student and there is no ideal teacher as well. So in the same manner, there is no ideal solution. These all are hypothetical, but of course, up to some extent, they follow Raoult's law. Is this clear to us? Good. Let's move forward. Now, after ideal solution, let's look at the non-ideal solution. What is non-ideal solution? Non-ideal solution will be solution which will not be following Raoult's law. For example, after ideal solution, let's look at non-ideal solution. Non-ideal solution means solution which will not be following Raoult's law. Okay. Now, when you are not following Raoult's law, so it could happen in two manners. Let's say I calculated by Raoult's law, vapor pressure is P. So either your vapor pressure will be greater than P or your vapor pressure will be less than P. Think is clear to us? Means suppose if I calculated from Raoult's law, vapor pressure is 100. So your vapor pressure, if you are non-ideal, so it could be greater than 100, let's say 110, or it could be less than 100, let's say 90. So based upon that, we have two type of deviation from Raoult's law. One is positive deviation and one is negative deviation. Now, what is the meaning of positive deviation? Positive deviation means when observed vapor pressure is greater than ideal vapor pressure, isn't it? Let's say ideal is 100 calculated from Raoult's law and observed is 110. So we will say we are having a positive deviation from Raoult's law. Now, what is the meaning of negative deviation? At the very same time, negative deviation is when observed vapor pressure is less than ideal vapor pressure. Let's say ideal vapor pressure is 100. So observed vapor pressure will be less than 100. Let's say 90, 95. So we will say we are having negative deviation from Raoult's law. Term is clear? Now let's check the quality of positive deviation and negative deviation. When we are having more vapor pressure than expected, what does it mean? Means our molecules like to stay in solution form or they want to stay in vapor form. Think, we are having more vapor pressure. That means our molecule wants to stick to vapor form or they want to stick to solution form. They want to stick in vapor form. They don't want to stick in solution form. That's what I have written here. Molecules have a lesser tendency to stick in a solution. Means they don't want to stay in solution. They want to stay in vapor form. So that is solute-solvent interaction. Solute-solvent interaction means AB interaction. What is AB interaction? AB interaction is formed when we add two different type of compounds. So solute-solvent interaction, which is AB interaction, it is not strong. If it was strong, so A and B will stick in solution. That means A and B solute-solvent interaction is weaker than solute-solute interaction. Means solute-solute AA interaction is very strong and BB interaction is very strong as compared to AB interaction. That's why solution formed is not existing in purely solution form, mostly want to convert in vapor. Now, if I am saying molecules are not liking to stick together, so what they are liking? They are liking to stay far. So when they are liking to stay far, so their volume will be greater than ideal or will be less than ideal. They want to stick far, so their volume will be greater than ideal. So delta V mixing this time, it will not be 0, it will be greater than 0. Are you getting this thing? Okay. Now, since we formed AB interaction, remember delta H mixing was interaction break plus interaction formed. Interaction formed was negative. Now, we are saying that AB interaction is weak. So it will release more energy or it will release less energy? It will release less energy. Let's say energy releases, let's say minus 50. So you know, when this interaction will be formed, for this interaction to be formed, you will have to break some strong interaction. Let's say their energy required for breaking interaction is 80. So tell me, delta H, when I will add these two, I will get positive or negative? I will get positive. So delta H mixing will be what? Positive. See, both are positive. When we have positive deviation, everyone is positive. Okay. Now, delta G mixing will be less than 0, delta S mixing will be greater than 0. We have already discussed this. Now, let's see some example. Now, generally, when we have hydrogen bonding at one place and we mix it with hydrogen bonding at another place, or any with polar solvent, we generally see positive deviation. See, example is H2O when mixed with alcohol. H2O when mixed with alcohol. H2O has hydrogen bonding. C2H5OH has hydrogen bonding. So tell me, whose hydrogen bonding will be stronger? H2O or H2O C2H5OH? Definitely H2O hydrogen bonding will be stronger. So that means if I will mix these two, so some H2O bond will be broken and some H2O C2H5 hydrogen bond will be formed. So H2O hydrogen bond is stronger than H2O C2H5OH hydrogen bond. Means AA interaction is stronger than AB interaction. Means AB interaction is weak. So molecule will like to stay in solution form or they will not like to stay in solution form. They will not like to stay in solution form because their solute form is more stable. So they will vaporize in order to stick together. Are you getting this thing? So they will produce more vapor. One more example is there. Let's say C2H5OH and acetone. C2H5OH means alcohol. Alcohol was having hydrogen bonding. Now you added some acetone in it. When you add alcohol in acetone, so some of the hydrogen bonding of alcohol will be broken. Why? Because we are going to form AB interaction now. C2H5OH interaction is what? Hydrogen bonding. And when you want to form AB interaction, means C2H5OH will have to break some hydrogen bond. Means it will have to break strong interaction in order to form weak interaction. Is it good or bad? Definitely bad. That's why these will not like to stay together. They will like to stay far from each other. Means they will give you more vapors. Clear? Good. Similarly, when you add polar with non-polar, with non-polar, so polar interaction is stronger. Similarly, non-polar interaction itself is stronger. But when you add polar with non-polar, so resultant interaction will be weaker. So you will get to see more vapor. That means positive deviation from Raoult's law or negative deviation from Raoult's law. Definitely positive deviation. Okay. Now let's see this negative deviation one more time. Now, our observed vapor pressure is less. Means molecule don't want to get vaporized. They want to stick in which form? Solution form. Means AB interaction, which means solute solvent interaction, it will be stronger, it will be weaker. It will be stronger. That's why they are sticking together in a solution, isn't it? Okay. Now, solute solvent interaction is stronger than solute solvent interaction is stronger than solute interaction. This thing is clear. Means molecule want to stick closer. That means volume observed will be greater than ideal volume or will be less than ideal volume. It will be definitely less than ideal volume. Means when you will add 50 ml with 50 ml, you will not get 100 ml solution. You will get less than 100 ml solution because molecule want to stick closer. So you will get around 95, 98, 99, maybe 99.9. Okay. So delta V will be what? Delta V mixing will be less than 0. Similarly, you are forming a strong interaction. Solute-solvent interaction is strong. So huge energy will be released. So huge energy will be released means delta H mixing will be what? Negative. And these two will be same. Delta G will be negative and delta S mixing will be positive. Okay. Now, examples. Let's see the example. Whenever you have OH group, phenol OH group and connected with nitrogenic base, any nitrogen base combining with OH group, so we always get to see negative deviation. Example is phenol combining with aniline. Phenol combining with aniline. So I hope you can understand that this would be somewhat like acidic. This would be somewhat like basic. Acid base interact very good. Are you getting this? Similarly, second example is if you have any H plus donor and you combine it with water, so you get negative deviation. Why? Because water is good acceptor of H plus. For example, let's say HCl with water. When you have HCl with water, you thought what? HCl will be dissolved in water. Similarly, HNO3 with water. You thought what? HNO3 will be dissolved in water. But there is one problem. When you add HNO3 in water, HNO3 gives us H plus. And that H plus reacts with water to form what? H3O plus. H plus plus water will give us what? H3O plus. That means, is it a good interaction? Is it a bad interaction? It is a very good interaction. They are even ready to form a new species. So that means solute-solvent interaction is very strong. So you will get to see less vapor formed as compared to ideal. Okay. One more example. Let's say this is very famous example. This is CHCl3, chloroform. Because of this 3Cl and their electron pulling in nature, this carbon will have so much delta plus on it. Eventually, this H will also hold some delta plus. Now, if you throw this chloroform with any compound in which nitrogen or oxygen are present. Nitrogen or oxygen, why? Because nitrogen or oxygen will definitely have some amount of delta negative. So, this delta negative and this delta positive on H, they will form a hydrogen bond. And this hydrogen bond will be stronger bond, na? So that means this interaction is strong. So you will get to see negative deviation. Okay, so please note everything from here. Okay, let's move to the next. Now let's understand the graphical representation of positive and negative deviation. Okay, think about this. Okay, when we have positive deviation, no one likes to stay in solution. See here in the graph, I made one dotted line. This is dotted. This is also dotted. And this is also dotted. These dotted lines are ideal case. These are ideal case when you don't have any deviation. But since we have positive deviation, that means every single individual compound will be producing more vapor as compared to real case. Means suppose ideally A should produce 50 vapor, B should produce 40 vapor. So A will produce more than 40 and B will produce more than 40, like that. Okay, so both PA and PB will be greater than its individual amount. Okay, so because of that, I will get more vapor pressure. This is real. This is real. PA plus PB real, and this is PA plus PB ideal. So this will be your positive deviation curve. Now let's move to the negative deviation curve. What negative deviation curve means? Ki everyone is giving less vapor pressure as compared to the ideal case. Okay. Now here, see, this is your PA, dotted ideal, dotted ideal, dotted ideal. Here you are getting PB positive. For PB you are getting less than expected. Here you are getting PL less than expected. So of course net will be less than expected. This is your PA plus PB real. Okay, please pardon the background noise. As you know, this video is being recorded at my home. So this is your negative deviation curve. Okay, let's move forward. Next thing is azeotrope. What is the meaning of azeotrope? Azeotrope means it is a solution which boils at constant temperature, or a solution which have same composition in liquid as well as vapor. Are you getting this thing? This is the meaning of azeotrope. Now, azeotrope are of two types. Azeotrope are of two types: minimum boiling point azeotrope and maximum boiling point azeotrope. Now, one important thing about azeotrope is a component of azeotrope cannot be separated by normal separation method. Means you cannot separate separate component of azeotrope. Let's say A and B are forming azeotrope. So you can never separate A and B by normal physical method. Okay, we need some special techniques, but those are not in our syllabus. Now, Azeotrope are of two types. One is minimum boiling point and second is maximum boiling point. Now minimum boiling point, it is formed by solution showing positive deviation from Raoult's law. Means whoever shows positive deviation from Raoult's law will form minimum boiling point azeotrope. And what about maximum? So maximum boiling point azeotrope will be formed by those solutions which show negative deviation from Raoult's law. Okay. One more thing. If you consider BP of maximum boiling point solution, it will be lesser than BP of any of the two component. Means let's say A and B are forming azeotrope. A has BP 60, B has BP 70. So azeotropic mixture or azeotropic solution will have BP even less than 60. Means it will have BP around 55, maybe 50, like that. Okay, so for this particular composition, a solution has BP less than BP of any of the two. In the same manner, for this particular composition, means whenever your azeotrope is formed, so solution will have BP more than BP of any of the two. Means let's say A and B are forming maximum boiling point azeotrope. So A has BP 60, B has BP 70. So solution will have higher BP than 70, like 75, 80, maybe 90. Are you getting this thing? So this is the definition of azeotrope. For example of minimum boiling point azeotrope, all those which show positive deviation, NCERT mentions one, the 95% weight, 95% by volume, ethanol and water solution. Means ethanol solution in which 95% by volume is ethanol. It is your example of positive deviation. It is example of minimum boiling point. Similarly, in case of maximum boiling point, 68% by mass HNO3 and water combination comes under the category of maximum boiling point azeotrope. Okay, let's move forward. Now for your understanding purpose, although it is not in the syllabus, but let's understand what is the meaning of minimum boiling point azeotrope and maximum boiling point azeotrope, and how does it work? What is the meaning of it as same composition in liquid and vapor form? Let's understand this. See, this is the graph for vapor pressure and temperature showing positive deviation. Okay, now for this composition, let's say point A, I hope you can see there is a maximum coming. Maximum coming means at this composition you will have maximum vapor pressure. When my vapor pressure is maximum, so in order to boil the solution, do I need more heating or less heating? I need less heating. So if more VP is present, means maximum vapor pressure is present, so at that time your boiling point will be what? Boiling point will be minimum. Are you getting this thing? Let me draw the graph corresponding to the boiling point. See, this is I'm drawing boiling point. Same curve but boiling point. Let's see this. Let's see this. And now see. This is your ideal case. See what I did? Wherever VP was maximum, I put that in minimum. Wherever VP is maximum, I will have minimum boil. Wherever VP is maximum, I will have minimum VP. Wherever vapor pressure will be less, I will have more VP. Okay. Now for a particular composition A, I had maximum vapor pressure. So this time I will have minimum boiling point like this, somewhat like this. See. Okay, this means this will be minimum. Means for particular composition A, solution will have BP what? Minimum. Okay, now this is boiling point of component, let's say X, and this is boiling point of component, let's say Y. Here let me write X, mole fraction. Here also it is mole fraction. Now let's see. I hope you understand if I have achieved a composition. If I have achieved a composition, and what I want to do, I want to separate the composition of A and B here. I want to separate composition of solution at this particular composition. At this composition, if I start heating, so see, boiling point of one component is X, boiling point of another component is Y, and boiling point of solution is less than either of X and Y. So who will boil first? Will it be X will boil first, or Y will boil first, or solution will boil first? Definitely solution will boil first. So what will happen? Let's say you have the solution. You thought I have A and B. A has vapor pressure, let's say 60, boiling point 60. B has boiling point, let's say 70. Now your solution has boiling point 40. You thought, okay, let's separate A and B by fractional distillation. You use your technique, we started heating. So solution will start boiling at 40 only. So the moment you will be reaching up to 60, you will not get any liquid here. You will only have all vapors, because entire solution will be boiled now. So you can't separate A and B by normal physical method. Regarding the same, similarly you can draw a graph for maximum boiling point azeotrope also. Okay, so we have covered this entire topic. Now your task will be go through the questions which I gave in the DP and find the question in NCERT as well. Try to solve them. If doubt arises, ask me. Okay, the rest we will discuss in the next video. Okay. Bye.